recording. Thank you. Yes, we can start.
Okay. So I'll begin then.
No.
Oh,
one moment, we have small formalities. Yes, please.
Namaskar. Honorable Professor Pushpak Bhattacharya, today's guest of honor, esteemed colleagues at CIL, friends and virtual participants. I take this opportunity to extend our warm welcome to Professor Pushpak Bhattacharya, Chair Professor of Computer Science and Engineering at IIT Bombay, to speak on multilingual computation, its indispensability in natural language processing. It is a great pleasure and a real privilege for all of us to listen to Professor Pushpak Bhattacharya on this occasion. The topic is of great interest for all of us. It is interesting to note that most of his area of research and contribution is related to language technology, and he is a well-known scholar in natural language processing and machine translation. He is one of the best NLP experts in India, an academician of global repute, and also has been instrumental in influencing artificial policy making in India through his participation in various government committees. We are thankful to Professor Pushpak Bhattacharya for agreeing to deliver the lecture on the occasion of 53rd Foundation Day lecture series organized by CIL Mysore. Some of his important quotes are: linguistic data is evidently available in the country, so linguistic work in India is always very relevant and full of interesting challenges. The excitement, energy, and passion for NLP come from linguistics. Important quotes from Professor Bhattacharya. Once again, we are thankful to Professor Pushpak Bhattacharya for sharing his valuable time with us. Welcome, sir. Namaskar. Over to you, ma'am.
Thank you, Professor Shailendra Mohan. Ladies and gentlemen, it's indeed a great privilege to have Professor Pushpak Bhattacharya with us. I would like to formally introduce him to this august audience and also for this lectures is to archive these lectures for future use by students and other interested colleagues. Professor Bhattacharya, as you know, he's a professor of computer science and engineering. At present, he's working in IIT Mumbai. His area of research is NLP and machine learning. I think I recall meeting him in 2005, first time in Mexico. I don't know whether he remembers it. He was there for a cycling conference, and that was on machine learning. That's how I met him there. And from then onwards, I've been observing his works and his research. He has been working on various topics, of course, and he held various positions as well. He was formerly director of IIT Patna for 5 years and president of ACL, Association of Computational Linguistics, in 2016. He is a fellow of National Academy of Engineering and Abdul Kalam National Fellow 2020. Professor Bhattacharya is also an editor of the Journal of Natural Language Engineering, published by CUP, and also an editor of AI magazine, Triple AI. He has varied degrees, BTech and MTech, and of course PhD from IIT Mumbai. He has been a visiting professor in various countries, United States, MIT, Stanford, and also in Grenoble, France. He has been lecturing on NLP in top national and international academic institutions and industries throughout the world. I don't think there is enough time to talk about his research and development. He has published more than 350 research papers, and he was also a key person in developing the Indo WordNet. That's again, there was an occasion where we again crossed our paths in Shillong and Pinewood Hotel. So recalling some good moments with you, and so nice that I could see you at least virtually now. His professional services also, he is a chairman of AI Standardization Committee of Government of India. He is a member of Governing Council of the Center of Advanced Financial Research and Learning, set up by none other than the Reserve Bank of India. We are very proud of you for having accomplished so much at such a young age. And also in 2010, he brought one of the top NLP conferences to our country, that is the Calling Conference. It's a very prestigious conference. He has been awarded with several fellowships and other awards, distinguished awards like H.H. Mathur Research Excellence Award, Manthan Award of the Ministry of IT, Patwardhan Award of IIT Bombay, BNM Award of IIT Roorkee. Quite a bit of awards, and his visibility is like he's there everywhere. When you talk about NLP in Indian languages, people say, where is Pushpak Bhattacharya? As simple as that. So with these few words, I once again welcome you to our institute virtually. I really hope to see you once in person here, and on behalf of the CIL and on behalf of everyone assembled here, I extend my warm welcome to you and invite you to deliver the 23rd lecture of this prestigious Foundation Day lecture series. Thank you so much. Please.
Thank you, madam. Am I audible?
Yes.
Okay, first and foremost, I am very privileged and honored to be part of this lecture series. And I would like to thank Professor Umarani for giving me this opportunity. And I see many stalwarts and my friends in the audience, Arul Muri, Professor Subbarao, Professor Sachadeva. Thank you so much for coming to this particular gathering. Now, I'll share my screen. So I've changed the title of the talk slightly. Multilingual computation in Indian languages actually is low resource natural language processing. So I'll beg your pardon for this slight change. This makes the main question very, it makes the main question stand out really in the discussions, because we are interested in doing natural language processing in a low resource setting. So what I present today is born out of the work of many PhD, masters and undergraduate students. I owe all these insights, findings, results to their hard work and a lot of dedication. Now, natural language processing is now a billion-dollar industry, but when we were doing natural language processing long time back, when we started it 20 years before, 25 years before, it was not so hot as it is today, to use a very popular expression. And its practical utility and its usage has become really all-pervading whenever there is an interface between human beings and computer. Now, the problem is that natural language processing with machines requires enormous amount of data, and we need innovative ideas to be able to do natural language processing, also called computational linguistics. And very interestingly, many of these innovative ideas come from deep insight into linguistics, and quite a few fundamental ideas from linguistics. So let me proceed. This is like preaching to the choir, but I would like to remind ourselves the Indian situation of multilinguality, the main streams of language that exist here. I grew up in the Northeast, and I have been exposed to Khasi language, which belongs to the Austroasiatic family. Professor Subbarao has done enormous work on South Asian linguistics and language. We have borrowed extensively from those ideas to create algorithms for natural language processing. And in terms of speaker population, some of the languages are within rank 10 in the world, like Hindi, Urdu, 5th, Bangla, 7th, Marathi, 14th, and so on. Now, this tree is important not only to students of linguistics, natural language processing researchers also have to pay attention to this tree, because there is this notion of language distance and language divergence. Some of these examples in the context of machine translation I will present to you as we go forward. Now, this tree is important in multilingual computation because we do what is called cross-lingual embedding and cross-lingual natural language processing by making use of these linguistic foundation of language distance. Now, in terms of practical impact, the reason why natural language processing draws the attention of the whole world, one of the reasons is this, that there are a large number of people speaking these languages, and their lives are impacted by technology which facilitate communicating, interacting, and making use of these languages. Now, natural language processing, one of the useful and established views of this area is this layered processing or pipeline processing. We start with computation on words, where morphology identifies the parts of the word, and these information is useful for part of speech tagging. The grammatical categories for the words are found out, and then shallow parsing produces small group of words which are meaning bearing, and they're important for example, question answering. Parsing produces the syntactic tree, dependency or constituency. Semantics does word sense disambiguation, identifies the semantic roles. And for large pieces of text, we have to be mindful of the discourse constraints, co-reference requirements, and also pragmatics. So this view of natural language processing is now well established, and it has correspondence with computational linguistics, especially layers of processing when we use deep neural networks. Algorithm designers in natural language processing again cannot be unmindful of this three-dimensional view of natural language processing, where on the language axis we have different languages with their properties and personalities, so to say, and useful problems like semantic role labeling, for example, for Marathi is useful for practical applications. But the final outcome of all this study is a piece of code which embodies an algorithm, and the underlying algorithm can be very complex. For example, deep neural network combined with, let's say, support vector machine, hidden Markov model, and so on. So I'm using these terms, I apologize, without defining them, mainly to bring home the point that natural language processing has become extremely computation intensive, requiring huge amount of data, lot of computing resources. And at the same time, error analysis and insightful algorithm design is impossible without understanding the linguistic properties and the language phenomenon. Now, ambiguity is rampant in natural language processing at every layer, and some of the ambiguities are really challenging and difficult, requiring either lots of data or extremely clever algorithm design. So this is an ambiguity illustrating the challenge in dependency parsing. So this sentence appeared in Times of India during COVID times, And Maharashtra reports increased COVID-19 cases. In this case, reports is the main verb. And once the main verb is identified and the heads and modifiers are put in place, the dependency tree is fine. But the interesting possibility, an interesting possibility exists where increased is looked upon as the main verb. In that case, Maharashtra reports becomes a multi-word, and increased is the main verb. COVID-19 cases is the object, and then this dependency tree gives rise to a very strange meaning, as if the Maharashtra reports led to the increase in COVID-19 cases. So again, I apologize for preaching to the choir. These kind of ambiguities are ubiquitous when we deal with language, and we have to mainly solve this challenge, the challenge of ambiguity. Now, ambiguity resolution requires data, and that leads to building classifiers which help resolve the ambiguity. Ambiguity can be at every layer, as I said. Now, pragmatic ambiguity gives rise to many interesting linguistic phenomena, including sarcasm, where we have done quite a lot of work. So if you look at this picture here, the text, wow, well done, is an expression of positive sentiment, but look at the body language. This actually is indicative of underlying negative sentiment. Now, positive sentiment and negative sentiment appearing together produces sarcasm. So we have latched onto this incongruity and designed algorithms for sarcasm detection. And in this case, the incongruity is also related to what is called the pragmatic ambiguity. Deep neural networks are extensively used nowadays for natural language processing. And it is hoped that a large number of layers in deep neural network actually correspond to different stages of natural language processing. Now, if I take these three words here, depending on where the pause is, it again leads to ambiguity. The question is, are dogs welcome or not welcome? Okay, so this ambiguity needs to be resolved through larger context. And this deep neural network actually takes the representation of the sentence layer by layer, producing representations. And at the final layer, we get the decision on the text which is input. So an example of this would be, let's say, sentiment analysis, where the sentence input in the first layer gets through all this processing, and finally a decision is made with respect to positive, negative, or neutral sentiment. Now, in this case, what we have to be sensitive to is the key role played by data and the processing of language data, sentences, phrases, paragraphs, chapters, and so on. And here, probability has come to play a very fundamental and important role. Now, I mentioned ambiguity resolution being the crux of the matter in natural language processing. Now, ambiguity means choosing one amongst multiple options. So this requires scoring these options and choosing that option which has the highest score. How do we get that score? That score is essentially a probability score. And the probability score comes from assuming some kind of distribution on the language data, which is given in the problem that is of interest. So data shoulders more and more responsibility. And typically, a neural network is harnessed to process this data. And this neural network actually does estimation of the underlying distribution. So this is the ruling paradigm now on natural language processing. So much so that multilinguality is looked upon as a shift in distribution from one language to another with its own parameters. So this I'll elaborate as we go forward. To take a simple example of how natural language processing is done these days, I take this example of machine translation through what is called the encoder-decoder network. So this is the French sentence which is input, Troya lapa de Grenoble, and the target English language sentence is 3 rabbits of Grenoble. Now what happens is that as the system goes over these words through a sequence processing mechanism, this is called recurrent neural network, then these words get encoded in the first layer, and the representation is fed into the second layer, where this decoder outputs the words which are the translations of words in this sentence, as well as decides the order in which they should be presented. So if this requires changing the syntactic order of the words, then the decoder does this through its own training on the language data. Now, machine learning plays a very important role here because the data is processed by a classifier, and for many tasks, like in other areas of AI, let's say image processing, scene understanding, and so on, in natural language processing also, data plus classifier is giving serious competition to human decision makers on language. Okay, so we envisage a world where computational linguistics and natural language processing would be done synergistically by language experts and NLP machines, which is trained on huge amount of data. Now, though machine learning has become a very widely used paradigm for natural language processing, there is a problem with such models. They lack what is called explainability. They're very robust. Now, many of us who have been doing natural language processing for several years now would recall how we would sit down on an NLP problem and think of devising rules to make decisions on the language data. If you are translating, let's say from French to English, then we would create a rule which will say that if there is an adjective-noun combination in French, then put the adjective before noun when you go to the English side, okay? Because there is adjective-noun inversion when you go from French to English. So such rules should be created one after another. There was a very large machine translation system called Systran, which had 200, 300,000 rules to capture various language situations. So such development of automatic machine translation systems would be very time consuming, and it would require lots of language expertise to create a robust system. Now this scenario has changed. You give to the machine examples of the NLP problem in terms of data, and very quickly the NLP system gets created. But the price to pay is that such systems are not really explainable. When we have a set of rules doing NLP, we can see how the computation proceeds, and we can explain the working of the system. Now the systems have become robust, but at the cost of explainability. Now, many of the work that I'll be describing today are being done in the Center for Indian Language Technology at IIT Bombay. This is in existence since 2000, and we have worked on almost all areas of natural language processing, believing always that linguistics and computation have to go hand in hand. We have a slogan in our lab: linguistics is the eye and computation is the body. Both lead to natural language processing. Now I come to the main discussion, and the discussion has two parts: machine translation and sentiment analysis. I may have to skip some of the subtopics depending on the time available, but let me first take the epitome of natural language processing problem, the problem of machine translation, which actually started the area of NLP. Now, machine translation involves translating from one language to another by computer. And the paradigms that exist for machine translation are, first of all, divided into two categories: knowledge-based machine translation and then data-driven machine translation. Under knowledge-based machine translation, we have rule-based MT, where we create various rules for reducing the divergence between the source language and the target language. And the other large paradigm is the data-driven paradigm, which is the ruling paradigm also today. Now here we have example-based machine translation, statistical machine translation, and neural machine translation. Now, one interesting point I have found out from my analysis of the situation is that for all these paradigms, there is an underlying A word, okay, which captures the essence of that paradigm. In rule-based paradigm, the whole responsibility is on accurate and complete analysis of the source language sentence. So it is analysis which is the crux of the matter in RBMT. In example-based machine translation, which was proposed in 1980s, the paradigm is based on analogy. So we make use of translation memory. Whatever phrase, words, sentences have been translated, they are reused in a new situation. Okay, so Ram writes with a pen. If writes with a pen has been translated before as pen kalam se likhta hai, then you would like to make use of this translation unit in future translations. Now, here the ball moves to the court of analogy detection. In a new sentence, you have to find out how many phrases and which phrases or which parts of the sentence have been translated before. And it is a retrieval process from the translation memory, which is involved in this. In statistical machine translation, everything begins with aligning the words. Okay, so Troya lapadi Grenoble, 3 rabbits of Grenoble. We have to align Troya with 3 and Lapa to rabbit and so on. So from word alignment, we can create phrase alignment to syntactic tree alignment, and from there the translation can be produced. And finally, today's paradigm on machine translation, which is neural machine translation. There is another A word. This is called attention. Now, attention actually captures dependencies between different parts of the sentence. So the gender marking on the verb, for example, Sita phal khati hai. So this gender marking of E is because of Sita. So the neural machine translation system pays attention to the gender of the subject, and through identifying this feature produces the correct gender marking on the verb. So it is attention, and attention is not only intra-language, attention is intra-language. So the neural machine translation system pays attention to the source sentence as well as target sentence. And how is that attention paid actually? It is paid through learning. Okay, so from previous examples of translation, the neural machine translation system learns which word corresponds to which word in the target language corresponds to which word in the source sentence. So you can possibly see the analogy between attention and alignment, but attention can be more complex and more sophisticated. So it is interesting that these 4 A words are the underlying main ideas in these 4 paradigms of machine translation. Now, today's ruling paradigm is neural, which is very data intensive. And this interesting graph, which was produced in 2017 in a paper by Cohen and Knowles, showed that as the data increases, the neural network-based machine translation system very quickly catches up with statistical machine translation. And after some time, there is no match. There is no competition between the 2 paradigms. Okay, so the neural machine translation system, Google Translate, Bing Translate, everything is now based on neural machine translation system. And these are very large systems with millions of parameters. The transformer-based system, for example, GPT-2, GPT-3, they have billions of parameters. And these parameters cause very robust systems to come into existence for machine translation. Just wanted to make sure that I'm audible and the screen is visible.
Yes, sir.
Yeah, okay. Thank you. Now, so analysis in RBMT, alignment in SMT, analogy in EBMT, and attention in NMT, these are the essential elements. Now, the challenge of machine translation is really the language divergence. Languages have different ways of expressing meaning. Lexico-semantic divergence and structural divergence, these are the two categories of divergence. So lexico-semantic divergence is for words, phrases, and so on. And structural divergence is mainly with respect to the syntactic order of words and lexical units in the sentence. So a long time back in 2002, we had a paper in Journal of Machine Translation discussing the English to Indian language divergence with illustrations from Hindi. And this was used extensively in creating a rule-based machine translation system for English to Hindi in the context of the famous UNL project, Universal Networking Language Project of United Nations. Now, we take an example of a sentence. This blanket is very soft to illustrate language divergence and language distance, so to say. So my pronunciation for Manipuri may not be completely accurate. I apologize for this. But this example is mainly to illustrate my point. So this blanket is very soft. Hindi translation is "Yah kambal bahut naram hai." Bengali is "Ei kambalti khub naram." Marathi "Ha kambal khub naram ahe." Manipuri "Kampar asi mon mon lawi." So we see different elements of language distance or divergence. And again, this is really preaching to the choir. But you see Hindi to Marathi machine translation will involve just word-to-word substitution. So if we cross the barrier of word sense disambiguation, then this is simply a matter of correct word substitution. So "Yah kambal bahut naram hai." "Ha kambal khub naram ahe." Bengali drops the verb copula, but introduces classifier. So this is a matter of divergence. "Ei kambalti," "Yah kambal." T is the classifier, which Bengali insists on for idiomaticity. And khub naram, and drops the copula. Okay. And in English, of course, the verb, this is SVO, and the divergence to be resolved is SVO to SOV for these languages. Manipuri is an interesting case, member of Tibeto-Burman family, where we have demonstrative pronoun and noun inversion. This blanket, "Yah kambal," "Ei kambal," "Ha kambal," in Manipuri, "Kampar ossi." And intensifier is captured by reduplication. "Mon mon lawi," soft, very soft. Manipuri also has verb copula. So from an analysis of this language data, we can create this kind of tree representation in terms of language distance. Marathi is very close to Hindi. Bengali is also close, but it has its own differences like classifier or copula drop. Manipuri is quite different, and Hindi, English are different in terms of syntactic order, let's say. So what is the implication computationally speaking? Computationally speaking, the implication is in terms of what is called the Vauquois triangle. So this triangle was given in 60s by a French physicist who took up the problem of machine translation in the context of Russian to English machine translation, which was important in those Cold War days between America and Russia. So here we we see a triangle called Vauquois triangle, also called Vauquois pyramid, where at the lowest level, the source sentence is taken up and passed through different levels of processing. And after we go up to a certain level of processing where the sentence representation is obtained, we do a transfer to the other side. This is the target language. And from this changed or altered representation, through NLG techniques, natural language generating techniques, produce the target language sentence. Now, "Yah kambal bahut naram hai," and ha kambal khub naram ahe, we can see that we do not need much analysis on the source side of the Walk-Word triangle. We can very quickly do a little bit of processing on the source sentence and then transit to the target language side and do natural language generation. And therefore, this is an easy case. Let us recall the language tree where Hindi and Marathi were siblings in the typology tree. And that is the inspiration for designing machine translation algorithms, because very low distance is involved in translation. On the other hand, we have to do quite a lot of processing in translating from Hindi to Manipuri, arranging for reduplication for intensifier, then inversion of noun and demonstrative, and so on. Okay. Now here there is an interesting point here. All these language phenomena we need to be aware of if we are doing rule-based machine translation system. All these arrangement of closing the language divergence will be done by data and machine learning, let's say the neural machine translation system, automatically. Okay. However, it is linguistic insight that helps us give emphasis to the kind of data that is fed to the machine, and also to do insightful error analysis. So the role of linguistics in all these data-driven natural language processing is to create the training data with wisdom, and also to do error analysis when the results come out. So Walk-Word triangle has been an important abstraction, an important backdrop against which machine translation systems have been created. So simplified Walk-Word triangle conceals many details, and essentially it is analysis, transfer, and generation framework. In rule-based machine translation, we indeed go through the whole NLP pipeline, starting from morphology analysis, pause tagging, chunking, vibhakti computation, named entity recognition, and do a transfer onto the target language side, and arrange for many computational tasks like the intra-chunk agreement, inter-chunk agreement, word generation, agreement feature insertion, and so on. Now, since we have been doing Indian language computing for a long time, creating natural language processing systems, we would like to document a few, common challenges when we do Indian language NLP. So there are these 22 major languages in India, written in 13 different scripts with over 720 dialects. Code mixing is a way of life in India. So, kyau ye hesitation? Hesitation is English. There is a very interesting gerandification. Gaadi chalawing. I have heard it myself. Tu kya kar raha hai? Gaadi chalawing. Okay. So this ing suffix added to chalana as the root. This is a very interesting and peculiar construction. Then there is absence of basic NLP tools and resources. English that way enjoys a very enviable position. There are so many tools and resources. There is absence of linguistic tradition for many languages. And then the script complexity and non-standard input mechanism. This really comes in the way of obtaining large quantity of data for training a machine. The transliteration itself is many times non-standard. Mango can be written as AM, AAM, or capital AM. Newspapers typically make use of proprietary fonts, so it is not necessarily Unicode based. Again, leads to loss of data, training data for machine learning. And then there are these challenging language phenomena like compound words, hasparana, morphology stacking, ghara samuchani, and resource scarcity. So these are only a few examples of challenges that are faced by Indian language, natural language processing research. So in 2014, when this statistical machine translation came, and fortunately through some support of MeitY, Minister of Information Technology, under the leadership of JNU, ILCI corpus was created. So 18 languages parallel corpora got created, something like 50,000 sentences, which is really small compared to what is used today in neural machine translation. But we made use of statistical machine translation in our lab and generated this particular table, which was reported in an LREC paper as a kind of Indian language machine translation experience. So many interesting things were observed in this experimentation. It was observed that the Indo-Aryan group of languages show good blue score for their pairwise translation. So Hindi Punjabi is very high, about 68 blue score, which is almost human level performance in translation. And of course, very domain specific for tourism and health corpus. When we go to the Dravidian family, the blue score drops dramatically. So from Indo-Aryan to Dravidian language family, the blue score hovers around 10 to 15, which was around 30 to 40 in within Indo-Aryan family. Within Dravidian languages, again, the blue score is really low, about 8 to 10. Then from Dravidian to Indian language machine translation, we found the blue score to be rising slightly compared to Dravidian, but again, nowhere near the Indo-Aryan group. And from English, of course, to Indo-Aryan group, the blue scores are typically higher, and Dravidian languages, the blue score is lower. Blue score, by the way, is a measure of performance for machine translation, and that is mainly based on n-gram matches. We match unigrams, bigrams, trigrams, go up to 4 grams, and then take an average of this matching score. So this actually set us to thinking, why does the Dravidian MT of Dravidian languages, why does it fall so drastically when you go from Indo-Aryan to Dravidian? And we understood that the main reason was morphological complexity and heavy agglutination. So one of the agglutination phenomenon, examples of agglutination phenomenon is in Marathi, Ghara Samor Chani. So Ghara Samor Chani means Ghar ke samne wale nahi. So it requires breaking these strings into small parts and arranging for their translation. So statistical machine translation at that time did not give us a way, but later statistical processing actually gave an instrument for handling this requirement. One could have done, morphology analysis and isolated the morphemes, arranged for their translation, but practical difficulties existed. Morphology analysis, creating a morphology analyzer is really, it requires a lot of investment in terms of language experts, funding, and so on. But statistical breaking up of long strings into small parts helped us. So, this really is mitigating the resource problem, and we understood that we have to make use of linguistic insight and artificially augment the resources, make use of helping languages to do translation. So there are 3 ways of artificially boosting the resource, 3 ways of handling low resource in natural language processing, the main theme of our discussion today. So we can do subword based natural language processing. We can break the words into characters, syllables, orthographic syllables, and the statistical method of doing byte pair encoding. What is the motivation for this? This example illustrates the motivation. Kha and unga together will give rise to will eat. And ja raha hai produces is going. Now you can do cross alignment and cross concatenation to obtain kha raha hai and jaunga. Though in the data we do not have this evidence of mapping, we have only evidence of khaunga going to will eat and ja raha hai going to is going. But from there we can arrange for kha raha hai to be translated to is eating. So this is insightful. Okay, this kind of cross concatenation and cross-lingual alignment actually helps us reduce the data requirement. We don't need the data of kha raha hai going to is eating. We can synthesize this from existing examples. So this is the subword based natural language processing. Then take help from another language. This is cooperative natural language processing. And use higher level language properties, for example, part of speech, sense ID, morphemes, and so on, So this is not possible without good linguistic insight and linguistic tools. Now, there is a trade-off though, there is a pitfall, NLP's law of trade-off. So when we aim for high precision, we have to sacrifice recall. When we try to solve the data sparsity problem, we may introduce ambiguity inadvertently. When we inject information for the natural language processing task, it may lead to topic drift. So this trade-off needs to be balanced out, and this balancing of conflicting requirements is done really by probability, which is why probability has become so important for us. Now, we carried out this kind of resource mitigation system development, resource mitigation-based system development. And the word-based translation, which produced blue scores, which are shown here, like Punjabi to Hindi is 69.97, already very high. But Punjabi to Telugu was 15.45, which is a low blue score. Okay. So with our subword-based and other resource mitigation-based ideas, we could improve these blue scores. So these subwords are characters. We break the word jaunga into characters, morphemes, ja and unga, syllables, ja, and ga, orthographic syllables which end in vowels, and byte pair encoding is statistically significant frequent strings. So this way the words were broken. And then when we did statistical machine translation, the blue score, for example, for Punjabi to Telugu improved from 15 to 16.78, about 8.61% improvement. Punjabi to Tamil improved by 15%, Punjabi to Malayalam by about 21%. So this was morpheme level translation. The words were broken into their morphemes. When you used byte pair encoding and did translation, then the blue score improvement was much more dramatic. Punjabi Telugu improved by 14%, Punjabi Tamil 28%, and Punjabi Malayalam 35%. Of course, in domain-specific situations, tourism and health. But this told us that if we break the word into its parts, okay, and establish this part-to-part correspondence, it can lead to improvement in the blue score and better performance. And by the way, this is the now ruling paradigm for neural machine translation. Another idea we investigated was factor-based statistical machine translation. This was back in 2009, where we embellished the training data with linguistic signals. For example, I ate mangoes. Here, I is agent, ate is past tense form of eat, and mangoes is the object, eat being a transitive verb. So these kind of semantic role information and morphological information were padded on to the raw parallel data, and these came as additional helpful signals for arranging for machine translation. So this is called factor-based statistical machine translation, goes back to 2007. And the interesting thing was with about 13,000 parallel sentences, which is laughably small, we could still get very respectable blue scores of up to 28, which was an improvement over the baseline by about 4 points. And our qualitative study showed that even the adequacy fluency scores also improved quite reasonably. And we essentially saw that the fine case markers were much better handled when we did this kind of factor-based machine translation. For example, this argetim marker ne, which was many times missed in the target language translation, came very accurately when we did factor-based machine translation. Then we thought of introducing other languages into the picture. We have source language and target language, but why not take help from a third language, which is possibly resource rich? So this is based on the following very intuitive idea. Pani in Hindi gets translated to jal. Now, to translate pani to jal, we need training data. We need evidence in the training data. But suppose no parallel sentence has this evidence of pani going to jal. On the other hand, pani going to water is there in parallel corpus of Hindi and English, and water going to jal in the parallel corpus of water and Bengali. So if we introduce English as what is called the pivot language, the helping language, then we can mitigate this data sparsity problem. Okay, the signals and evidences absent in training data can still be handled by introducing a helping language. So we did an interesting example with Indian languages and Mauritian Creole, but the theory was provided by this fundamental paper on pivot-based machine translation, also called bridge-based machine translation, by Wu and Wang in 2009. And here the key idea actually comes from the basic laws of probability theory. So it's an argmax-based computation. I apologize for being slightly technical here, that we go from English source sentence to French source sentence. Now this is controlled by the probability of alignment between English words and French words, English words and English phrases and French phrases. Now here you can introduce more the evidence from other languages through what is called marginalization. So this is a very nice framework where the mathematical power of probability theory was used to introduce another language in a principled way to help the two languages, source and target languages. So the approach is called the triangulation approach. So we have what is called the source to pivot phrase table obtained from source to helping language parallel corpus, and pivot to target phrase table obtained from pivot to target parallel corpus. And if we are fortunate to have little bit source to target phrase, source to target parallel corpus, then we have the source to target phrase table also. So three phrase table, three alignments are used here to create the source to target machine translation system. And this modeling or the mathematical framework of which evidence to take from where and how to score between two conflicting evidences. So if a word is translated into two different words, how to resolve this tie by making use of probability, all this is very nicely worked out in this paradigm. Now, I'd like to make an interesting point here that this very little source to target parallel corpus is in today's world called few shot machine translation. Few shot, that is a few parallel sentences. And if there is no source to target parallel corpus, then this is called zero shot machine translation. So zero shot and few shot NLP are the popular phrases applied to many natural language processing tasks. So we did this interesting experiment of translating Mauritian Creole to English. This was also a requirement. There was a postdoctoral fellow coming from Mauritius to our lab, and the government of Mauritius had asked him to work on Mauritian Creole to English machine translation. But the problem was there was very little parallel corpus between Mauritian Creole and English. So we thought of using French as the helping language. Why French? Mauritian Creole and French have a lot of linguistic similarity, a lot of vocabulary overlap. For example, French avion is also avion in Creole, meaning aeroplane in English. And French to English is extremely resource rich. There are millions and millions of sentences. Did not exist at that time, but currently there are millions and millions of parallel sentences for French to English. So much so that French to English machine translation system competes very well with human translators, human professional translators. So we made use of this kind of helping situation, help from French, and we could obtain, a lot of improvement in the blue score, especially for short sentences when translating from Mauritian Creole to English. And this idea was carried forward, and later this researcher who visited from Mauritius actually created a machine translation system between Creole, Mauritian Creole and English, which apparently is used by the government for administrative, for translation of administrative documents. We applied this idea to Indian languages machine translation. The task was English to Hindi machine translation. And when we had many Indian languages brought in as helping or pivot languages, then we could improve the performance given the amount of corpus. So if you look at this graph here, if we fix the x-axis, then y-axis, on the y-axis we find improvement in accuracy as we introduce pivots. And the best help was obtained when we introduced Punjabi and Urdu as helping languages for English to Hindi machine translation. And those were reported in top-level conferences. Now, we have been mentioning neural machine translation quite a lot. All machine translation systems have now moved into the neural framework. The basic idea is simple. We take the source sentence and pass it through what is called the encoder. The encoder converts the whole sentence into a set of numbers, a vector of numbers, of course, maintaining the word boundary. And this representation is now fed into another neural network. This is called the decoder. And it produces the target language sentence. I read the book, Maine Kitab Padhi. In this framework, of course, the long distance dependencies cause a challenge. So that's why one introduces the attention network. And the attention network now has given rise to the use of transformers very heavily in neural network. And from 2016 onwards, Google Translate, Bing Translate, they all became neural and transformer based, giving rise to very high quality machine translation for a number of language pairs, French, English being very notable there. So we could obtain high blue score for Hindi, Marathi in neural machine translation with small amount of corpus. Hindi, Punjabi very high, 63, Punjabi, Hindi 68, and so on. So in the Indo-European family, even with small amount of corpus, we could obtain very respectable blue scores. So since data scarcity is always a problem, the whole world is now investigating the problem of unsupervised neural machine translation. So suppose there is no parallel corpus, can we still do machine translation? So we also contributed to this effort, and this is the unsupervised neural machine translation, where there is no parallel corpus absolutely. But we have monolingual corpus of the source language and the target language. If it is English, Hindi, we have huge amount of monolingual corpus of English and Hindi. Now, what is the basic idea? The basic idea is called isometricity. So we have what is called the word embedding created from large amount of corpus. Now, very simply put, the word embeddings are points in an n-dimensional space where this dimension, n dimension, is decided by the requirement of the problem. Here we make use of what is called projectivity. That means if we have, let's say, 100,000 words in our vocabulary, then we present to a system vectors of length 100,000, but only one of the components, one of the bits being one there. And we insist that given an input, let's say book, the neural network should produce the context words. For example, book goes very frequently with the verb read. Book can also go with the word expensive. So we capture the distributional similarity and train a neural network with this distributional environment information. So present to the neural network the word of interest and insist that the neural network produces the context words automatically and thereby obtain a representation for book. Why that representation works for downstream NLP tasks is another discussion, which we can do later. Now, all languages can create their word embeddings. Now, interesting thing is that you can build a bridge from language to language. Okay, so this was really seminal work in 2015-16 onwards, where one could build these kind of bridges, so much so that if you take a common representation for multiple languages, then in the common representation space, all these representations become language independent, and words with similar meaning hang together. They are clustered together in this space. So dog and kutta, tiger and bag, billy and cat, they will be together. So all those words which mean billy, they will be together in a cluster. So this is called the isometricity property. And this is a very strong, and foundational idea for reducing data requirement when you do machine translation. Well, I think we can see intuitively that this has a chance of working. Of course, the technique has to be designed properly. So we make use of what is called multilingual embedding. Embedding is the vector-based representation of words, phrases, and so on. Now we have also mask-based embeddings, okay, which is seen in T5, GPT-2. I'm mentioning names again. Sorry for just mentioning names, but all of them actually try to cross the language barrier, at least at the word level, okay, by putting all these words together whenever they have similar meaning in a multi-dimensional space. So if we do so, then we can really proceed towards unsupervised machine translation. Because you see, word-to-word correspondence has been established through cross-lingual embedding. Now, the only thing that needs to be taken care of is managing the syntax. An SVO language, when translated, might become SOV. So arrange for the verb to go to the end. Okay. Then adjunct, divergence, and an inversion of head and modifier. All these things can be arranged by what is called denoising. Now, the idea of denoising is also interesting and simple, where we give different permutations of a sentence and insist that the neural network corrects that syntax order. It produces the correct syntax order. So by giving a sentence whose word order has been disturbed and insisting that the canonical order arrives at the output layer, we can train a machine to learn the syntax. So I think all of us are appreciating this point, that we have managed to create lexical correspondences through cross-lingual embedding, multilingual embedding. And we have been also able to arrange for syntactic order divergence to be managed through what is called denoising. Okay, all these are simple ideas, but they are very crucial for unsupervised or supervised machine translation with very little data, also technically called zero-shot and few-shot machine translation. So denoising and back translation has again become a ruling paradigm for unsupervised machine translation. So we did this work. We had a paper in ACL a few years back, where in a completely unsupervised manner, we could obtain blue scores in the range of 15 to 20. And this is completely unsupervised, no parallel data, only huge amount of monolingual data. And qualitatively also, we could see that we can obtain translations. So if you see this French sentence, whose reference translation is preparation to manage a class in a North American and Quebec context. The baseline system produces the build-up to manage a class in an Australian, which is quite a lot of junk, I would say. But in our system, the preparation to handle a class in a Latin American context, at least a good syntax order and some amount of content from the source sentence could be captured. So this we saw across European languages and later for Indian languages too. Let me proceed to our more recent work on unsupervised NMT with filtering on back translation. So in unsupervised NMT with back translation, what is back translation? We take the monolingual corpus of the target language and pass it through a shared encoder-decoder framework. Okay, we do not have time to go into details, but the main idea is this, that we take a sentence from the target language, from the monolingual corpus, pass it through a partially constructed unsupervised NMT system, and the output that comes out is added to the parallel corpus. This is a pseudo-parallel corpus. We are not given actual data, we synthesize the data. Now here a lot of low quality translation is also obtained. Now our recent work shows that we can filter out bad quality translations and add to existing parallel corpora in an incremental manner and obtain good blue scores. Now here, our main contribution lied in giving a loss function which is sensitive to the quality of the parallel corpus. Okay, I'm keeping the discussion at a higher level without going into those mathematical nitty-gritties, but these actually could achieve a state-of-the-art performance, in fact, better the state-of-the-art performance for neural machine translation. And we could show that for established work like song and Lample and Connew and so on, with filtering, we could improve the numbers in most cases. Okay, so the second row in both these compartments is showing the blue score compared to the baseline performance. Okay, so this part, sorry to be hurrying over. We have done extensive work on English to Marathi machine translation system, and this is a low resource setting and very, very multilingual in character. So here we have done data augmentation through subwording, phrase table injection, taking help from statistical machine translation, back translation, combined corpus, and so on. And all these have led to a well-performing English in the machine translation system. Okay, we collected corpus from many sources, and here we have seen that on very standard benchmark data, we get a blue score in the range of 15 to 20. By way of some qualitative example, the toy train from Kalka to Shimla is considered as the most beautiful rail line in India. This whole thing is also available as a web service. If time permits, I can give a demo later. So Marathi baseline, Kalka te Simla पर्यंत धावणारी रेल्वे भारतात सर्वात सुंदर रेल्वे लाईन मानली जाते. Now here we have a little more accurate translation, little more specific phrases. Kalka पासून सिमला पर्यंतची टॉय ट्रेन भारतातील सर्वात सुंदर रेल्वे लाईन मानली जाते. So toy train is captured when we use English Marathi data, of course, but use embellishments, okay, linguistic embellishments on the training data. So this was consistently observed for many, many situations. Demo, I'll see if I can give later. And there are qualitative examples for this. So let me hurry through this and go to the next part. This part I'll very quickly finish. I know I'm running out of time. I changed the problem totally into a different area of NLP called sentiment analysis. We have many, many years of work on sentiment and emotion analysis, which is also important because e-commerce companies, organizations, government, political parties, all these entities want to know what is people's opinion about their performance and about their entity. Amazon, for example, would like to know what people are saying about their service in a multilingual context, not only English. They want to know, for example, what somebody in Bihar is writing about Amazon in Bhojpuri. So for all that, of course, which are very important practical problems, we need to first situate the problem formally and rigorously through a definition. So sentiment analysis is concerned with identifying the sentiment of an opinion holder H at a time T for an object with respect to a feature F. Okay, so for example, if I take this long sentence, I love the songs in the movie, though only the cast was liked by my brother, who said the director was of the opinion that the storyline, which is from a novel by Shakespeare, will be lapped up by the public. So a long and convoluted sentence, and it is important to identify the triples in this form. I love the song, brother like the cast, director like storyline, public lap up storyline. And one should be mindful that Shakespeare is not looked upon as an opinion holder or sentiment bearing person. So this takes us to information extraction and dependency parsing forms a foundation. Semantic role labeling forms a foundation. So these are important NLP tasks. So sentiment analysis also is a multidimensional problem. We have to be mindful of language and culture. Different languages express sentiments differently. CJK languages hardly use very intense and strong adjectives. It's very intense qualifiers. They hardly use that. And again, the features which fit the machine learning system can be bag of words, syntactic dependencies, discourse features. The machine learning system can be rule-based to very, very data-driven like generative models, deep neural networks, and so on. We may have to make use of resources like dictionary, ontology, and so on. So sentiment analysis is indeed a complex and multidimensional problem, and we have explored this area extensively. Now, multimodality is now looked upon as essential for sentiment analysis. So facial expressions, body language, they need to be captured in a multilingual framework. Now, if one wonders, how does one combine image with text? Okay, that's a very valid question. This combination is done because of the neural computation paradigm again. So neural network looks upon everything, every input, whether it is image or text or speech, anything, as a set of numbers. So one can combine a vector obtained from an image with a vector representing a piece of text. So if I have this sentence, this movie is dumb, then this is negative sentiment. And also look at the facial expression. This thumb down, it can be an emoji given by this writer or the communicator. And all this can be combined in a multilingual, multimodal framework to build powerful sentiment analysis systems. Emotion analysis is little more complex than sentiment because sentiment has to deal with only 3 classes: positive, negative, neutral. Emotion analysis has finer levels like anger, disgust, happiness, and so on. So the basic emotions are looked upon as happiness and sadness. Psychologists have given more categories like Ekman's emotions: anger, disgust, fear, sadness, happiness, and surprise are used extensively in computational linguistics. Pragmatic emotions adds 2 more emotions: anticipation and trust. And in India, we have a very long tradition of dealing with, analyzing emotions. So there is this Navarasa theory, which actors, dancers have to master to depict through their expressions. So we studied all these frameworks, and Plutchik's wheel of emotion again has an interesting facet that in this wheel, the emotions close to the center are very intense, and towards the periphery, the intensity decreases. Also, between 2 petals, we have combination emotion. For example, joy and trust gives rise to love. And ecstasy is more intense than joy. Serenity is much less intense than joy. So these 8 basic emotions are put in a wheel, and their different intensities are obtained through terms representing these low intensity or high intensity emotions. So we have been working, as I said, since 2000 on sentiment analysis, handling many, many different kinds of sentiment analysis problems. And one of our most recent research is in sentiment and emotion in dialogues. This is also a very practical problem because organizations like Air India, airlines, insurance company, embassies, they have chat bots who interact with their customers and stakeholders in a language that is human, which has empathy. So those kind of things are necessary now, and interaction must have empathy and emotion sensitivity. So we did a problem on dialogue act classification, which is sensitive to sentiment. So dialogue act classification is concerned with the intent of the speaker. So a chatbot is interacting with a human user. So at every turn, the chatbot must understand the intent and also the emotion. So our contribution was the introduction of emotion in meaningful dialogue generation. So each turn is primarily a question, a statement, or a request for action. This top-level classification, the chatbot should be able to do. And then there are these finer categories in each of these: question, statement, and request for action. And then there are these 8 or 9 or 10 emotions which we obtain from work of psychologists. So there are also non-verbal features. So we resort to multimodality. I give an example here. These 3 words, ha, ji, ha in Hindi, can denote agreement, ha, ji, ha, or disagreement, ha, ji, ha, in a sarcastic tone, would indicate disagreement. So we created data set. These days it is very important. The data set, when created by a research group and made open to the other researchers, is a contribution. So we have enriched a dialogue turn data set with emotions. We have combined emotions and dialogue turns classification with the data, and it is also multimodal and multitask. We have shown that if we do dialogue turn classification along with emotion classification, the performance of the system is better when both the tasks are done in a single task manner. So multimodality and multitasking, these two together gives rise to a powerful system. So we worked with the data, and an example of dialogue with turn classification is this. A says, so to B, so do you go to college right now? This is a yes/no question. And then are you, but they cannot finish the sentence because B interjects before this, before the completion, says yeah, which is the yes answer. And then B says it is my last year. This is categorized as statement. So all these are dialogue acts, which you see on the second column. So dialogue act classification is the first important task for conversational artificial intelligence agents. So in this emoji data set, we have taken care of greetings, apology, command, question, answer, agreement, these kind of different categories of dialogue turns, as well as emotion. So here is some distribution information of the data. So in this data, for example, the statements actually form the largest category. And on the emotion side, neutral again forms the largest category, followed by happiness, followed by anger, then frustrated. And in the dialogue turn category, after statement come questions and opinions. So, we saw from the data that multimodality is important. So if you take this sentence, that's very amusing in it. It can give an impression of being an agreement statement, but the audio shows that the tone is sarcastic, and the facial expression shows there is slight anger in the expression. So then we have to revise the opinion about the emotion and the category of the dialogue, and the response will have to be appropriately generated. The chatbot should be sensitive to both emotion and the category of the dialogue. So we made use of multimodality. We made use of text features, audio features, video features through many different tools, which the neural NLP. We built a fairly complex neural network, but it is logical also. So there are 3 compartments in the input: video, text, and audio, which are combined in the next compartment, and we take pairwise signals, okay, text and video, audio and video, and so on. And then finally pass it on to what is called the softmax layer, which is based on probabilistic decision. It classifies the dialogue properly, and it gives the emotion also. So again, it is customary to report numbers, and we have found that we get the best performance when we combine text, audio, video all together. And when we combine dialogue as classification along with emotion response. So when the dialogue and emotion are both considered, then the chatbot's response is of much better quality. So qualitatively, for example, she is not Larry's girl. This is the true level is disagreement. When we do multitask-based classification and emotion recognition, this comes out at DAG, disagreement. But the single task system produces the label as statement. So this is not a simple statement. It is a statement with disagreement. So those kind of qualitative studies also we have done. So let me summarize my presentation, which was on low resource natural language processing, making use of multilingual signals. So several techniques have been explored and demonstrated for their efficacy. We have seen trace table injection. This has great potential to boost the BLUE score. So this is where statistical machine translation and neural machine translation work together. We can harness the monolingual data with back translation, forward translation, and that produces, again, a good performance. Morphological and word features which come from linguistic signals and linguistic analysis can also be of great help. So the conclusions and future work are as follows. Data is needed for quick system development and robustness. We really do not see people sitting down and creating rules for doing natural language processing. They do so when the data-driven system, the machine learning-based system, displays low performance on some language phenomena. For example, maybe the clause translation is not coming out properly. So let me investigate why clauses are not handled properly. Okay. So we have seen many times that this adjectival modifier, which is a clausal modifier for noun, and which should become participial modifier in the target language, that mapping often does not come out properly. So this kind of spotting of the actual problem requires a lot of linguistic insight. NMT ensures fluency and syntactic goodness. This we have observed very consistently. The whole neural machine translation community has seen this, that in neural machine translation, the syntax is taken care of very well, though the adequacy is many times low. So, for example, the named entities are not translated properly. The target language gives a different name in the translation. And low resource sentiment and emotion analysis needs multimodality. This is quite established. We have to catch signals from speech, video, image to do low resource sentiment analysis. And then there is no way out other than various tricks for ameliorating the data hunger. The future lies in cross-lingual, multilingual, word embedding, and their exploitation in downstream NLP tasks. Now, however, here is a trade-off which is insightful and foundational. NLP is a task in trade-off, really. If we have too much of information coming from, let's say, subwords and multimodality and multitasking and so on, it can introduce ambiguity inadvertently. And if those signals are too little, then we will encounter the problem of sparsity. So we have to tread a middle ground, which Lord Buddha had propagated long back, maybe over 2000 years before. So whatever I said is linked as research papers from my homepage, and we have contributed many resources, tools, data for natural language processing, especially focused on Indian language processing. So thank you very much for your attention, and I'll be happy to take any questions. Thank you.
Thank you, Professor Bhattacharya, for your insightful talk. It was fantastic to listen to you. In the last 1.5 hours, you took us into a wonderful journey of machine translation, especially coming, like the field itself is, of course, only 70 years old. You have taken us into a wonderful journey by showing us how neural networking can enhance the tasks what people, both computational linguists and NLP practitioners, have been working on for decades and decades. You beautifully summarized your own work, so I would not like to take much time to do that. I would like to open the talk for discussion. Professor Subbarao has raised his hand. Yes, Professor Subbarao.
Thank you. Thank you, Uma, for arranging this wonderful talk. Thank you, Professor Bhattacharya, whom I call Pushpak ji.
Thank you.
We have been known each other for a long, long time. I don't know, maybe 20 years or more.
Yeah.
All right.
Quite
So it's it's a wonderful talk, listening to the whole thing. And I must tell the audience that Pushpak ji is one of the persons in India, perhaps the person, who envisages the symbiotic bond between linguistics and computer science and natural language processing. He was the one who openly declared that these two have to go hand in hand. We are not two different, what you call, the banks of the same river. We have to meet somewhere, and he took care of this point very well by interacting with linguists. And I must say, in the course of his journey, he has acquired enormous knowledge of linguistics. I think syntax. I think he knows as much syntax as I know, even more than that.
No way.
So I'm very happy that he brought linguistics and NLP and computational linguistics together. And I really enjoyed this talk, Pushpakji, and I hope to listen to you again. So whenever there is some kind of semi-technical talk like this, let me know. Because if it's too technical, I'm out. But this talk is very good, very understandable. Thank you very much.
Thank you. Thank you very much.
Yes, Parameshwari.
Yes, sir. Yeah, thank you, ma'am, and thank you, Professor Pushpak, for beautifully explaining the state of the art as well as your contribution in the field, your team's contribution in the field of NLP over the years. So yeah, my question is something like that. See, these days machine learning relies mainly on big data, right? But the poor performance directly implies that either we need the improvement in terms of annotation when we are working with supervised model, or improvement in the data size for the unsupervised model. What's your opinion on this type of inconsistency in the output? Sometimes, when we work with when we see multilingual model, error in one language pair directly can be reflected or can be seen in another language pair. Right. So, do you still think that there is the coupling of knowledge base on the top of NMT may solve some of the issues and may provide more fidelity in the output?
Okay. Yeah. Thank you. Thank you for this question. So this really takes us to this trade-off point which I made. So we have observed very interesting errors when we introduce a helping language or a pivot language in machine translation. So I remember clearly when we were doing machine translation, and the word kajal was involved, okay, and byte pair encoding converted kajal into ka and jal, because ka is very frequent in the data, jal is also frequent. So kajal got translated as of water. Okay, so this was wrong because subwording produced morphemes whose translation was obtained, and this translation was not really called for. When we introduce other languages, we have to encounter the problem of false cognates. Okay, one of the popular examples is shiksha in Marathi, which means punishment, and shiksha in Hindi means education. So when we mix language data, these problems do appear. But then the question is, why are people combining language data? Okay, if I want to do machine translation of Hindi, Marathi, why would I combine Punjabi data with the parallel data which is available? This is mainly because of the data scarcity problem. Okay, we want to ameliorate the training data scarcity, and this is a kind of act of desperation. So when this happens, there are these wrong signals which come in. False cognate is a very important problem there. Now, your question is, how do we mitigate this problem? How do we solve this problem? Okay, so there is no free lunch, as they say. This is the price we pay for augmenting the data. Now, what is acceptable in this situation is that if the pros outweigh the cons, okay, I can live with some amount of translation being wrong, but by injecting Punjabi data, if I get good performance on Hindi Marathi machine translation, why not? Okay, if the performance improves from 30 blue score to, let's say, 35, why not? Okay, so this is the stand which is taken by the practitioners, and you are also right that post editing would mitigate this problem. I mean, after the output has come, a knowledge-based system which has learned from the post-editing training data, which is, by the way, also an important research area these days. A rule-based or a machine learning-based post-editing system would correct the error. Okay, so the summary of my answer is that we have to live with this kind of errors which are introduced due to injecting of data in trying to solve the data scarcity problem.
Yes, thank you. But if you look at any layman looking at the output, they may not find the kind of research or the effort that are going behind this whole research, right? You look
Right.
at the language output as a human out. They try to compare it to human output. I think that mindset need to be changed.
This has been the fate of whole of AI. Since AI tries to mimic human performance, and since many of these performance are commonplace and natural and spontaneous for us, when we try to emulate this on machines, then human beings who are not in the field lose patience and say, "Ye log kya kar rahe?" So this is the fate of AI, I would say.
Yeah. So machines are not going to replace, but they are going to facilitate the human.
Right.
I think that has to be. Yeah. Thank you, Professor Pushpak.
May I ask a question? I mean,
Yeah, please.
Pushpak, I mean, I'm really interested in multilingualism also. And so for instance, when we are talking about, say, I may not be able to understand full of Marathi, but I have lived in Pune. But while, say, for example, trying to make sense of Marathi, not only is my Hindi lending a helping hand, my Punjabi, which is, say, a word like Changla and Changa from Punjabi, they will go and help me. Even my Sanskrit that I've been introduced to, in schools and all that. So it's several languages come to the fore. If I've been exposed to, say, some Marathi or Odia, maybe all of them become allies together, cognitive, for me to extract, because the mind optimally utilizes what is present in itself. I mean, it would like to draw on, it doesn't want to draw boundaries that this is a language A or B or C. I mean, that's a construct of ours that we are. So the tapping of cognitive resources from within, where you're optimally simultaneously, or if I'm, for example, going into Malayalam, I may not have heard of it much. But if I know some Kannada and if I know a bit of Tamil and maybe some Sanskrit, all of them simultaneously as are lending themselves towards my being able to suddenly crack the language there. So in that sense, the whole idea of multilingual competence, the nature of it in our mind, all the models that we are trying to do. I mean, there was this hesitation about trying to mimic what the humans do. But to my mind, even what humans do, that also needs to be examined thoroughly from within, and what's going on in what's the nature of our own competence when we know several languages.
Sure. I totally agree with you. And in fact, there is this neuromorphism, I think, which is another area of research where brain signals are also fed into the neural network. Okay, so this is man-machine synergistic problem solving, and these EEG, EMG, these also are now numbers which are added to the data which is present outside. And coming to this point of multilinguality, it is indeed really helpful to know, for example, Bengali if you want to understand Assamese, Orientals, because there is so much of vocabulary.
Yeah.
Okay, so this intuition is indeed captured in the neural network-based NLP. The only problem to be solved there is the problem of false cognates, mainly. Okay, and also nuance shifting.
No, but you see, I mean, let's, for example, you gave that example of Shiksha in Marathi, and I'm not very sure. Say, the word hinsa in Kannada doesn't get used the way I use it in Hindi or Punjabi. Hinsa. Here, in Kannada, would use it for difficulty. When this is a very difficult job, then he'll say, "Pada himse." So they use that himse. But at the same time, there is an element of cognateness even in that. I mean, when you were talking of punishment and lessons and things like that, you can't divorce the notion of education being given through punishment away from it. So it's not as if it's fully false. I mean, they are really far apart, the meanings, but there is a connectedness that you can still discover. In fact, when we do things like polysemy or whether it's something else, there are two separate items. Or the basic problem I'm saying, trying to ask myself, I mean, you are party to what I'm lending my mind to. Is monolingual competence any different from multilingual competence in any substantial ways? In the sense that even when I'm trying to discover, say, one lexical item is different from the other, I'm using all my phonetic devices, I'm using meaning devices, I'm using syntax and all that to tap and set one apart from the other in my mind. I'm doing actually something very similar even when I'm doing the second language, or third language or something like that. I'm looking into the phonological properties of that items coming in. I'm examining perhaps its syntax. I'm perhaps examining. So in some sense, there is a common universal properties of the mind are at work in discovering from A to B to C. I mean, there is something more interesting, intriguing going on in our minds, right?
Absolutely.
It's not as if you suddenly become, just because you know several languages, there is an extra element that you may think you have added. But in some sense, the original element of universal processing of languages never stopped. I mean, that is continuously available even in multilingual competence. And it's not, I'm trying to ask myself, what is it qualitatively different between the two?
Right. Yeah, I mean, I really do not have very good answers to this. The only point I think I can make is that the mixing of multilingual data for a computer has now become very commonplace. Okay? And when we do so, we also apply what is called this byte pair encoding. I understand I'm going to a much lower level of abstraction, but this byte pair encoding actually captures the common substrings. Okay, so these common substrings undergo transformation into different word forms in different languages. Like khana, kha is the root word, khawa in Bengali, khana in Hindi. Okay, now when we go to the level of this kind of common substrings of languages, okay,
Right.
this is one handle. This is one step towards the universal language platform that you are talking about. Okay, I'm taking a computational view, but monolingual competence versus multilingual competence, a very interesting question, of course.
Vivek Tripathi had a question. Are you
Thank
there?
you, ma'am. Yes. Thank you, sir, for such an insightful talk. I learned so many things about the development done in the translation. So I am particularly working on Hindi, and I am trying to do its semantic analysis using the formal logic.
Okay.
So when I was trying to see the researches done in this field, I was not able to find more of it. So did you happen to come across such research which is using the truth semantic logic for Hindi language, or any researcher who is creating the logic rules for the Hindi itself?
Not for Hindi, but the closest field which maybe answers some of your questions would be the field of natural language inference and text entailment. Okay, so you can read papers by Bill McCartney. If you write to me, I'll be able to send you a few references. Okay. But this is for English. And the goal is to be able to do natural language inference. So to take two sentences, one is called the text, other is called hypothesis, and see if the hypothesis is consistent with the text. So this has been handled in completely data-driven manner through training data of text hypothesis pairs, and also through these logical formalisms where they are converted into first order logic form, and then you do inferencing based on that. So if you write to me, maybe I can send you some references.
Sure, sir. I will write to you. My following question, I have one more following question, if that is allowed.
Yeah.
So when you were talking about the encoding and decoding as a method of translation, this came as an intuitive idea to me, whether it's possible or not. Maybe you can give me some insight that we are using some semantic and syntactic rule to encode a language, let's say Hindi itself or English itself, and then using that logical language or logical rules to decode it in target language. Do you think is it possible?
Oh, yeah. I mean, but here the encoding decoding is used in a very, very technical sense, in a very specific and constrained sense, actually. So encoding here means that we take the word, you get the vector of the word from a large corpus, and then these word vectors which form a sentence, okay, are passed through what is called a recurrent neural network. Okay, so this recurrent neural network at its final stage produces a set of numbers which represent the sentence. So whether it is possible or not, well, the applications seem to prove the efficacy of this paradigm. Okay, so you can do translation based on this encoding decoding framework. You can do classification. That means you can do sentiment and emotion analysis on these encodings. You can do fill in the gap. You can do question answering, summarization, all on these encodings of sentences. So the answer to your question is yes, it is possible, and it is being done actually for many NLP applications, and in a multilingual fashion for many languages.
Thank you so much, sir.
Any other question?
I have an inquiry from Professor. You have a very good department of Sanskrit, and Mahesh Kulkarni ji is there, no? He works in the IIT in Mumbai.
So Malhar Kulkarni. Yes.
Malhar Kulkarni, yeah.
Yes.
Are you two departments working together on something?
Professor Malhar Kulkarni is one of my closest collaborators.
Oh yeah, because I would thought that the whole idea of people have been giving us very fond impression about how Ashtadhyayi, the exposure that I have about its computational nature and all that. Are we tapping into that as a resource collectively? Yes. Are we mining it together?
Right. Like this Shabdarupa, Dhaturupa, they only give rise to morphology analysis. Yeah. And Professor Malhar Kulkarni and I were involved in this Indian language wordnet creation. Oh, wow. He created the Sanskrit wordnet, and we had built the Hindi wordnet before.
I'm so happy that these are coming together, because the idea is bringing people together across disciplines, across this thing. This whole idea is about breaking barriers that we have created for ourselves. It's like that. Fantastic. Yeah, thank you so much.
Thank you.
Thank you. Any other questions? Yeah, Professor Pushpak Bhattacharya, I have a couple of questions. I would like to, first of all, it was a very interesting talk, and I was very happy to see that how you are using machine learning, coupling it with neural network, which is very data intensive, of course. Yes. But my concern and worry after seeing the numbers of the blue scores of Dravidian, I was just wondering, see, number one, nowadays I don't work in computational linguistics. Nevertheless, I keep track of what's going on. So people talk about not very much positive about using blue scores as a good metric, mainly because it's not giving us the overall picture of the translation quality. And of course, you know very well, it does mostly string matching algorithm. But now the Dravidian situation, when you give examples, it was easy, like you did the ordering of Hindi to Bangla. There is an insertion of a classifier, and then how some small changes are taking place. So this reminds us very clearly we need to enrich our machine learning or data mining work with more of semantic and pragmatic input as well, because the semantic load and the pragmatic load, if we are going to do it in the training data, which you also said on your own, you said it is based on only 2 domains. I'm more giving you a feedback and comment rather than a question, but I'm just expressing my concern here. So number one was, can we rely only on the blue scores to measure this performance? That is the first question. And since you have given data from 2 domains, tourism and health, there are technical terms in this kind of domains, which has definitely some complexities when it comes to semantics and pragmatics. Because they are not simple domains, not like the day-to-day life domains. So that could be, so that is one question I have. And the second question is, it's related, though you said you're using denoising in unsupervised machine learning, I was wondering, can we augment it with some anomasiological approaches from lexical semantic theories? For example, you're taking words and you're going, I saw the network, small network, what you showed. Maybe some other day I would like to have a virtual meeting with you and look into your network, because you had dog, tiger, cat, and small examples, and you're looking for word collocations. I was wondering, instead of using the semasiological approach, what you're doing, if we do the reverse, or maybe a hybrid of it, going from semantic concepts and mapping onto words, may help you to see increases in the blue scores.
Okay.
That's
So yeah, good question. So let me answer both the questions one by one. The first question is blue score good for Indian languages? So these many MT groups all over the world have been asking this question. How good is blue score? Because the blue score is so intuitive, it almost borders on naivete. So looks like, it's a very naive approach. So what is done in blue score is that you have that machine output and you have the reference translation. Now you take unigram matching. So do word by word matching and find out and collect this number of matches. Then you take 2 consecutive words, which are bigram, then trigrams, and go up to 4 grams typically. So we collect these number of matches and take their geometric mean. So why geometric mean? That is another story. Now, this is essentially matching of unigram, bigram, trigram, and quadrigram. So what happens is that when you go to higher order n-grams, that is consecutive 4 words or 3 words matching, this captures the syntax pretty well. And whereas unigram and bigram, they capture vocabulary matching. Now, the point is that a machine translation output can match a number of reference translations, or the source sentence can be translated in many different ways. So typically, the blue score is more effective when we have multiple reference translations. Now, you're right that for Dravidian languages, and we have seen it for Marathi, Oriya also, where there is some amount of agglutination, is blue score a good measure? No, it is not. So that's why we have introduced what is called the subword-based blue score. So we convert the source sentences and target sentences into substrings using byte pair encoding, and then do neural machine translation on this. So same byte pair encoding algorithm is also used on the reference translation. So you do matching not at the token level, but at the subword level. So that captures the adequacy fluency situation much better than word-based blue score. Okay, so the answer to the first question is that subword-based blue score, where the words are broken into their morphemes, statistically significant morphemes, gives rise to more trustable and acceptable blue scores. That was one. Second is that the Dravidian language blue scores are low, so why not introduce more signals? By the way, those numbers that I showed were much older, and we have from the groups from South India who are using neural machine translation, the blue scores are much better. So do we make use of syntactic signals and semantic signals? So this has been happening. For example, if we take statistical machine translation, which is the baseline system is based on word alignments and then phrase alignments, it has been possible to do syntax-based statistical machine translation, where you apply dependency parsing or constituency parsing on both sides, and then arrange for alignment of subtrees, and that gives rise to much better system performance. This has been done in statistical machine translation. So syntactic tree-based neural machine translation is also happening. There is a different paradigm, different technique. It is called recursive neural networks. Okay, so this is happening. This is taking help from syntax. What about semantics? Okay, some amount of semantics helps is already taken at the word level, because we are creating word embeddings which are based on distributional similarity. So cat and dog will be similar in their representation, and cat and, let's say, table will not be as similar as cat and dog. So this distribution similarity is captured. Now these captures what is called the syntagmatic signals. Okay, the signal that is there in the syntagma. We also introduce what is called knowledge graphs into the deep learning system. For example, word nets are introduced into a deep learning based natural language processing to capture the paradigmatic relations. So all this is happening, and you're very right in suggesting use of semantic, syntactic, and lexical signals. And all this is happening to an extent. Lexical signals are definitely captured very well. Syntactic, if we have parse trees on both languages, we can do that. But the unfortunate situation is that very few languages have their dependency or constituency parsers. And other semantic signals like making use of paradigmatic knowledge along with syntagmatic knowledge is happening when we integrate knowledge graphs with deep learning.
Thank you. So it was, I mean, I do have other queries, but I think we are running out of time. But
Yeah.
I would like to be in touch with you again and explore this further, because even your second part of the talk, the sentiment and emotion analysis raises a lot of interesting observations from many. And of course, you rightly said that multimodality and multitasking gives rise to a powerful system. But even for this, like, I'm very happy to see the stage-wise development over the decades in your team's work. So now you're also exploring pragmatics with this sentiment analysis. That's very interesting. But it would be nice to have a large database of pragmatic tags. I don't think people are doing it.
Yes. Pragmatic tags, yes.
Yeah, so people are talking about sense tagging and sensivals and other systems, but time has come for us to look into pragmatic tags, which are culture specific, because emotions, I can, like right now, I just want to be online. I can smile and say, hell with you. Or I can be very quiet and say, I love you. So these are things like, how do you do it? How do the forensic linguists also interpret these emotions? It's a very interesting field, and I'm very happy you touched upon it. I think we will continue the journey with you. The CIL would love to have some more lectures from you on sentiment analysis, and also see how we can connect this with you're talking about low resource languages, and also talking about less resource languages like endangered languages or the non-scheduled languages. So I think we have a lot more to discuss with you. Maybe we will get in touch with you, the director, and I will write to you, and we will be in touch. So thank you so much for your wonderful talk. You kept us with your blue scores. You kept us glued for 2 hours. Thank you so much.
Thank you. And Vivek, you can write to the address that you put on the chat box. Yes.
Namaskar, sir.
Namaskar.
Thank you.
Okay, so I'll sign up there. Thank you very much. Thanks, everybody.
Yeah, thank you, everybody. Thank you, Professor Subbarao, Professor Sachdeva, Professor Shailendra Mohan. So many were there, Professor Sharma, and many more. All the young colleagues, Parameshwari, many people were here, Harold Moli, all my dear friends and colleagues, and CIL project people and staff, and also some colleagues from other parts of India. Thank you very much for sparing 2 hours of your wonderful day with us. Once again, on behalf of the CIL, we would like to thank Professor Pushpak Bhattacharya for being with us today and for delivering an excellent talk. Thank you so much.
Thank you. Bye.